Hi everyone, my name is Gaurav Gupta and I am from VIT Vellore. Today we are going to study about fiber optics. In 1977, Schultz invented the fiber optics through a telecommunication. John Tyndall first observed that telecommunication can also be done through bent wires. So what is optical fiber? An optical fiber is a hair-thin cylinder fiber of glass or any transparent dielectric medium. The fiber which are used for optical communications are waveguides made up of transparent dielectrics. Its function is to guide visible and infrared light over long distances. The larger the bandwidth of the larger the transition frequency is going to be. That's the main point. So then how the information is sent? First, a source of information sends the info to the electrical transmit, which then sends electrical signals to the optical source, which converts the electrical signals in the form of light waves, which are then transmitted with the help of optical fiber cables. Then at the receiver's end, the photodetector converts the light waves back into the electrical signals. There are mainly two types of photodetectors: LEDs and LDs. LED stands for light emitting diodes, whereas LD stands for laser diodes. At the electrical stage, the electrical signals are then about to reach the destination. So what is the need of optical fiber cable? Why can we just transmit the signals in the form of electrical signals? So what the advantages of fiber optic technology is mainly that it can carry much more information, much higher data at much higher data rates, and it is immune to any electromagnetic noise, unaffected by any atmospheric agents like moisture, and it's much more less in weight and flexible than compared to any of the coaxial wires available. The structure of optical fiber consists of mainly four components: core, cladding, buffer, and jacket. The core is the region where the light is transmitted. It is entirely made up of glass, whereas cladding is either made up of glass or plastic. It adds a certain amount of strength to the wire, and it reduces scattering loss from any of the discontinuities in the core material. Buffer coating: plastic coating that protects the fiber made of silicone rubber. The typical diameter of fiber after coating is about 250 to 300 micrometers. The jacket or the sheath is especially a plastic coating that provides shock and abrasive resistance for the fiber. Its thickness ranges from 250 to 1000 micrometers. It is not involved in the actual transition of light. The working principle. The working principle of optical fibers is total internal reflection. So what is total internal reflection? When a ray of light traveling from a denser to a rarer medium such that the angle of incidence is much greater than the critical angle, the ray reflects back into the same medium. This phenomenon is known as TIR, or total internal reflection. In an optical fiber, the rays undergo repeated number of TIRs or until it emerges out of the other end of the fiber, even if the fiber is bent. Any discontinuities or imperfections at the core cladding interface would result in refraction rather than total internal reflection, which would lead to either dispersion or attenuation of the signals, which would be explained later on. The acceptance angle. The acceptance angle is the angle at which the light waves enter the optical fibers. If the light waves enter at an angle larger than the acceptance angle, the TIR will not be performed, and hence the light waves will not reach its destination. To propagate the light beam down the optical fiber, the light beam at the core and the cladding interface must take an angle less than the critical angle. From Snell's law, it can be stated that n sine theta A equal to n1 sine alpha C. Here alpha C is theta C. Here theta is this, alpha C is this angle, and theta C is a critical angle. So sine theta equal to n1 sine 90 minus theta C. Sine theta equal to n1 cos theta C, and then cos theta C can be converted back into the form of sine, and then we would get sine theta A as under root n1 square minus n2 square. Here n1 is the refractive index of core and n2 is the refractive index of cladding. Any rays which are incident onto the fiber core at an angle greater than theta A will be transmitted to the core cladding interface at an angle less than theta C, which I stated earlier. Thus, for rays to be transmitted for the total internal reflection within the fiber core, they must be incident on the fiber core at an angle less than theta, as discussed earlier. So, the classification of optical fibers. Optical fiber is classified into two categories based upon the number of modes as single mode fiber and multi-mode fibers, and based upon the refractive index as step index fibers and a graded index optical fibers. Here the mode word understands about the amount of optical path in an optical fiber. So what is single mode fiber? In single mode fibers, only one mode can propagate through the fiber. That means the light waves only propagate in one direction. There is neither dispersion or degradation, therefore it is suitable for long distances communication. It has large bandwidth, but it's largely expensive, due to which results in less use of this type of technology. Multi-mode fiber. It allows a large number of modes for light ray traveling through it. The core diameter is approximately 40 micrometers and that of cladding is 70 micrometers. The relative refractive index is also larger than the single-mode fibers. As the light rays travel in many directions, it leads to dispersion and attenuation of signals. Moreover, multi-mode fibers cannot be used for longer distances. On the basis of refractive index, optical fiber can be classified in two ways: step index optical fiber and graded index optical fiber. Step index for optical fiber, the refractive index of core and cladding is almost constant. The light ray propagates through it in the form of meridional rays which cross the fiber axis during every reflection at the core cladding boundary. Whereas in the graded index fiber, in this type of fiber, core has non-uniform refractive index that gradually decreases from the center towards the core cladding interface. The cladding has a uniform refractive index. The light rays propagate through it in the form of helical rays. They never cross the fiber axis. Losses in optical fiber communication can be described in three categories: attenuation, scattering losses, and dispersion, as it can be seen in the image. First, here the macro of the losses due to bending, scattering losses, and absorption losses. Now attenuation. Attenuation determines the maximum transmission distance prior to the signal restoration. The optical fiber cables become especially attractive when the transmission losses of fibers were reduced below those of the competing metallic conductors, which is less than 5 decibels per kilometer. Signal attenuation in optical fibers is usually expressed in the forms of units of decibels. Here, dB stands is the attenuation coefficient, which is equal to 10 log 10 Pi upon Po. Here Pi stands for input optical power, whereas Po stands for output optical power. The attenuation coefficient can be written as alpha dB into L. Alpha dB is the signal attenuation per length and L is the fiber length. Now, types of what attenuation consists of: intrasonic absorption and extrasonic absorption. Intrasonic absorption is caused by interaction of the propagating light wave with one more major components of glass that constitutes the fiber material composition. These losses represent a fundamental minimum to the attainable loss and can be overcome only by changing the fiber material. Whereas in extrasonic absorption, the impurities ions absorption is caused by the presence of minute quantity of metallic ions such as Fe2+, Cu2+, Cr3+, and the OH- ion from the water dissolved in the glass. The OH- ion from water vapor in the glass leads to the absorption peaks at 0.72 micrometers, etc. The broad peaks at 1.24 and 1.38 micrometers in the first curve are due to the OH- ions. The good news is that OH- ions absorb band is narrow enough that ultra-pure fibers can achieve losses less than 0.2 decibels at 1.55 micrometers. The scattering loss. The scattering losses occur when waves interact with a particle in a way that removes energy in the directional propagating waves and transfers it to the other directions. The light isn't absorbed, just sent in another direction. However, the distinction between scattering and absorption doesn't matter much because the light is lost from the fiber in either case. There There are mainly two types of scattering: linear scattering and non-linear scattering. For linear scattering, the power that is transferred is directly proportional to the power in the wave. On the other hand, for non-linear scattering, there is a frequency shift of the scattered light. Now we will come to Rayleigh scattering, which is also a form of linear scattering. Rayleigh scattering can be defined as scattering in the small size parameter region. Scattering from larger particles is explained by the Mie scattering for an arbitrary parameter x. Here Mie scattering is not in our syllabus, but can be explained later on. Rayleigh scattering depends on the specific type of material, but on the size of the particles relative to the wavelength of light. The loss due to Rayleigh scattering is directly proportional to 1 upon lambda to the power 4 and obviously decreases rapidly with increase in wavelength. Bending loss. Bending loss are frequently encountered problem in the context of waveguides and in particular in fiber optics. There are mainly two types of bending losses: micro bending and macro bending. Micro bending is caused by poor cable design, whereas macro bending is commonly caused by poor installation or poor handling. Now we will come to dispersion. The number of optical signal pulses which may be transmitted in a given period, and therefore the information carrying capacity of the fiber is restricted by the amount of pulse dispersion per unit length. This is called as dispersion. Model dispersion in multimode fibers. Multimode fibers can guide many different light modes since they have much larger core size as compared to the single mode fibers, as discussed earlier. Each mode enters the fiber at different angles and thus travels at different paths in the fiber, which leads to dispersion. Since each mode ray travels a different distance as it propagates, they arrive at different times at the fiber output. So the light pulse spreads out in time, which can cause signal overlapping so seriously that you cannot distinguish them anymore. Now comes the material dispersion. Material dispersion is the result of the finite line width of the light source and the dependence of refractive index of the material on wavelength. Material dispersion is a type of chromatic dispersion. Chromatic dispersion is the pulse spreading that arises because of the velocity of light through a fiber depends on its wavelength. Waveguide dispersion. Waveguide dispersion is only important in single mode fibers. It is caused by the fact that some light travels in the fiber cladding compared to most light travels in the fiber core. Since a fiber cladding has lower refractive index than fiber core, light that travels in the cladding travels faster than that in the core. So now, what are the applications of fiber optics? In defense, used as hydrophones for seismic waves and sonar, as wiring in aircraft, submarines and other vehicles, and also for field networking. Data storage, used for data transmission. Telecommunications, fiber is laid and used for transmitting and receiving purposes. Networking, used to connect users and servers in a variety of network settings and help increase the speed and accuracy of data transmission. Industrial and commercial uses, used for imaging in hard-to-reach areas as wiring where EMI is an issue, as sensory devices to make temperature, pressure and other measurements, and as wiring in automobiles and industrial settings. For broadcasting, broadcast cables companies are using fiber optics cables for wiring CATV, HDTV, internet, video on demand and other applications. In the medical field, fiber optics is used for a process called the endoscopy. Fiber optics endoscopes are pliable, highly maneuverable instruments that allow access to channels in the body that older semi-grid instruments cannot access at all or can access only at great discomfort to the patient. Composed of multiple hair-like glass rods bundled together, these instruments can be more easily bent and twisted, and the intense light enables the endoscopist to see around corners as well as forward and backward. Accessories can be added to the instrument that makes it possible to obtain cell and tissue samples, exercise polyphase and small tumors, and remove foreign objects. Two of the parts of the fiber optics in the endoscopy is one for light to illuminate the inside of the patient, another for a camera to send the images back to the doctor. In the end, I would like to conclude that there are some negatives of using optical fiber communication system in terms of splicing, coupling, setup expenses, etc. But it is an unavoidable fact that the optical fiber has revolutionized the field of communication. As soon as computers will capable of processing optical signals, the total arena of communication will be opticalized immediately. So thank you for listening me, and with this I end my presentation. Goodbye.